Okay, so factoring. It's going to be kind of a series of videos. I have a few factoring videos just in general. This particular video is going to cover the factoring of difference of squares. If you've seen my previous videos, then you know that I have about 4-step process that I go through every time I attack one of these. And the first is I ask if it's in order. And in order, I mean if I look along the terms, that the terms are decreasing essentially by 1 as I move through the terms. You can't see it in here, but if there's a missing term, it's actually got a 0 coefficient. So there's other ways to do differences of squares without memorizing, but you can do it through if you input that missing piece. So that's the order. The next thing I do is I attempt, and this is a requirement, I attempt to factor out the greatest common factor. Factor out the greatest common factor. Step number 3, there's a list of 5 different special factorings, and I try, but if I don't remember them, I don't remember them. It is what it is. So a pair of them are called perfect square trinomials, and I'll be doing that in a subsequent video. Another is the difference of squares, which is what we're going to be covering in this video. Squares. Wow, my writing is terrible today. And then the third is another pairing, which is the sum or difference of cubes. One of these days I might get a fancy stylus pad, that way I can write a little bit better. We'll see. Alright, and then fourth, everything else fails, and we just attempt to factor the long way. Now, these next 2 videos are going to be concentrating specifically on factoring difference of squares and then perfect square trinomials. So I've designed them so that every time we do a problem, it's only going to use the first 3 steps here. However, once you're done, you have to go back to every one of the other factors and check it to see, is it in order? Can it be factored out, or is there a greatest common factor that can be removed? If so, you probably didn't remove it right in the first place. But then step 3, and you go through the entire process for all of them until you can't do it anymore. If all of these steps outside of the order fail, so you put it in order because you can always put it in order. If any of the other 3 steps, or if all of the other 3 steps fail, then we are considering this to be not factorable. It's kind of a misnomer because it can always be factored. It just might not be factorable in a nice sense, meaning with solutions that involve only integers or rational numbers. So keep that in mind. It can be factored, it just might not be the way you want it to be. Alright, here we go. Let's take a look at what it means to be the difference of squares. And I didn't put the absolute genericiest, if you want. I did include a number out in front of the x squared. So now, if there is, you have to check to make sure that it itself is a perfect square. So the difference of squares breaks down into the sum and the difference of their roots. That means that if the first thing is a perfect square and the second thing is a perfect square and you're subtracting, that's the hint, shh, don't tell anybody, then you can split it up this way every single time. So as a quick example, if I take a look at 4 and 100, they are perfect squares. 4 is a square of 2, 100 is a square of 10. So I can split this. Whoop, I say 2 and then I write 4. Look at that. I can split it into 2 and 10, 2 and 10. You notice the x's are split as well. And then it's just plus and minus. The order of the factors is irrelevant because remember, multiplication can happen in any order. And I know some of you are going to be like, oh, but it's got to go left to right because that's what the order of operations says. except it's commutative, so the order of operations is largely irrelevant at that point. It just has to happen before you add or subtract and after you work through exponents. So, understanding beats memorization every time. All right, so then we take a look at this and we say, hey, could we have done something? And we say, oh boy, you know what we didn't do? We didn't go through our 4 steps. And so, number 1, is it in order? Yes. Number 2, factor out the greatest common factor. 4. We could have factored out a 4. And the reason I say that is because if you look, 2 and 10 share a common factor in each. Yeah, we screwed up. So I'm going to redo this because I don't like it. So I'm going to factor out a 4. So that's going to be 4, and then I have an x squared minus 25. And now I've factored it. So I look at the things to see if they're perfect square trinomials, that sort of thing. This is still a difference of squares, and that factors down to x squared. Not x squared, ding dong. X plus 5 and x minus 5. And then this 4 that's out in front, yeah, you got to bring him down too. That, ladies and gentlemen, is the answer. All done. The end. To do this for really, I would have to go through and I'd have to check x plus 5, x minus 5 to see if they if they themselves are factorable again. But they're not, so I'm just kind of letting it go. All right, let's do another one. Remember your 4 steps. We're going to do that on this one here. All right, so we have 9 and 729. Step number 1, is it in order? And the answer is yes. It is in order. Okay, well, now let's try something else. Well, 9 is a perfect square. Is 729 a perfect square? Some of you might be going, I don't know. Well, in that case, take the square root of it. And if you take the square root of it and you come up with a whole number, then it's a perfect square. It does turn out that it is a perfect square. It's 27 squared. But 27 has a factor of 9, just like the first thing. Which means 729 must also have a factor of 9 in it. So if we do this properly the first time right out of the gate instead of the last time we did it, then what we can do is we can factor out this common factor of 9, and that's going to leave us with x squared and minus 81. And then we just simply ask ourselves, hey, is this thing inside perfect squares? Well, x squared is perfect square. 81 happens to be 9 squared, so we can go ahead and split that up. And now we have x plus 9 and x minus 9. And we bring this 9 down. And so we've got 9 times x plus 9 and x minus 9. Okay, those quantities then we have to look at one more time and say, hey, are they factorable? And we notice that 9 is a perfect square. So we may be able to factor this x squared, or this x minus 9, except that x itself is not a perfect square, or at least we don't think it is. We don't know because we don't know the value of x. However, if it isn't a perfect square, then we can't do anything. If it is, we could have, but the worst case scenario is we can't. So we let it go. So this would be the answer for this. Again, remembering bring out that greatest common factor. It makes life easier anyway. All right, this next one's a little tricky. So it's 9x squared plus 100. And some of you will be going, oh yeah, you just do this exact same thing. So there's no common factor between 9 and 100. And so when you do it, you end up with 3x plus 10, 3x minus 10, and life is good. Except we have a slight issue. When we go back and check this, I have 30 minus 30 is 0, which is good. I don't have a 0 here, but 10 times negative 10, this is 9x squared minus 100. It's not the same. As it turns out, the sum of squares in the real numbers is not factorable. It takes the power of the complex number. If you know about the complex number, then take a look at the next little bit that I show you. If you don't know about the complex number, completely ignore what I'm about to do until I move on to that next problem. Okay, so now if I know about the complex, then I know that x plus I, x minus I actually expands into x squared minus I squared, but I squared is always positive 1. I'm sorry, I squared is negative 1, but subtracting it is positive 1. That's x squared plus 1. So the sum of squares can be broken down in the sum and difference of the roots involving I. So if I were to break this one down, it'd be 3x plus 10I and 3x minus 10I. And now that you're multiplying what are known as the conjugates, and so if you are dealing with if you've already learned about the complex numbers, you should know what the word conjugate stands for, and that's the reverse sign. So if we have addition in the first one, its conjugate is subtraction. When you multiply the conjugates together, you end up clearing the imaginary terms. So you take this 10, multiply by that negative 10, you get negative 100, but I times I is I squared, and I squared is a positive, negative 1. So you have negative 10, or negative 100 times negative 1, which gives you positive 100. This is equal to 9x squared plus 100. If you don't believe me, you can always throw it in your calculator and just go, and it'll do it. But, or you can just take my word for it. All right, we got one more, and this kind of looks weird, so let's take a look at this. Okay, so 81 and 1 don't share any common factors. It is in order. Those two things can kind of be done separately. Now, the order, I will say, is a more advanced topic. The order really doesn't matter as much, at least not yet, but it's if you continue on in your math, it might be easier to see other shapes, other constructions, at least through their equations, if you put them in order. The one that comes to mind is the circle. If you haven't learned about that yet, the circle's equation can be quite nasty looking, especially if they are shifted. But anywho, so we look for greatest common factor, which there is none other than 1. Now we can go ahead and attempt to factor this. Well, 81 is a perfect square. 1 itself is a perfect square. It is its own square. So this is going to become 9x plus 1 and 9x minus 1. If we didn't know that, you're like, well, wait a minute. What? I don't. It's hard for me to memorize stuff. I would love to say it's hard for me too, but my math teachers in high school were like, hey, know this, memorize this. Okay. And so I just learned it. It's, yeah, I don't explain it. I just like, yeah, I know what that is. What does it mean? I don't know. Can I go now? So, yeah, that's kind of the attitude I had. We are missing a term. If we insert that term with a 0 coefficient, we're not changing the value. We're not changing the worth of this little expression here because we're adding 0, because 0 times x, no matter what x is 0. What this will do, though, is it allows us to then factor it out yet a different way. And if you've seen some of my previous videos on factoring things that don't have a leading coefficient of 1, I factor it this way. So I have 1 in 81, I have 3 in 27, and I have 9 and 9. And those are the only factors of 81 that I'm aware of, and then 1 and 1 are the only factors of that. So I'm looking for 2 pairings, and so if I pair, I have to multiply 1 from the front, and 1 from the back, and 1 from the front, and 1 from the back, and then I have to do this thing to it. If, when I do this multiplication and I subtract the products, I get 0, good, I found the numbers, and they are the front and back numbers of my 2 factors. That's what makes it fun. In this case, 3 times 1 is 3, 27 times 1 is 27, and if I subtract them, I get 24, which is not 0. The only time it works, actually, for really, is when I use 9 and 1 and 9 and 1. So I'm going to have 9x and 1, 9x and 1, and this sign tells me that my signs are opposite. Which means one of them gets a positive, one of them gets a negative, and it doesn't matter which one does it. So again, it doesn't matter if I happen to not know this rule. I can do it in other ways. But you still have to know how to do it the other ways because they work more times than this does. So I would know the other way first. Anyway, that's all of my examples in this video involving difference of squares. If again you come to it and you can factor either of these two factors again, then you must. Otherwise, your teacher's going to get all kinds of angry, and mostly because it's wrong, but there could be other reasons. All right, hope that helps.